It has been reported that the probability that an individual will develop schizophrenia over their lifetime is 0.004. In a random sample of 3,000 individuals, it was determined that 17 developed schizophrenia. Is there evidence to support the claim that the proportion of people who will develop schizophrenia is different from 0.004 at the alpha equals 0.05 level of significance? So we're going to go through and do this problem with the classical approach and the p-value approach. Some problems are going to work through and ask you for one versus the other, so we're going to work through both of those methods there. So the first thing we're going to do is write out our null and alternative hypotheses. So our null hypothesis here, again, is h sub 0 colon. Alternative starts with h sub 1 colon. And we're testing a proportion. So 10.2 is all about testing proportions. So here we have this here. And let's highlight some important information. So we want to know, is it different from 0.004, the alpha equals 0.05, and 17 out of 3,000. So there's our important information. So P is equal to 0.004, and then our alternative is P is not equal to, they just said is different, 0.004. So there's our null and alternative hypotheses. So the next thing we need to do is determine whether we can actually perform our test. So we need to go through some steps and make sure that we can actually perform our test. So before we do that, let's write down our important information. So we have x is equal to 17, n is 3,000, and alpha is 0.05. So let's go through and make sure that we can actually perform our test. So the conditions we need to check to test a hypothesis regarding the population proportion is that the sample is obtained by a simple random sample. So we're okay there because it says in a random sample. And we also need to make sure that the sample values are independent of each other. Well, for testing for schizophrenia, those are independent from one from another if we're truly talking about a random sample. And then we also must check that n times p naught, which is the p-value that, well, I don't want to say p-value, is the population proportion in the null hypothesis here. So n times p naught times 1 minus p naught is greater than or equal to 10. So once we check those conditions, we can proceed with our test. So let's check that. So 3,000 times 0.004 times 1 minus 0.004. So let's type that in our calculator. So 3,000 open parenthesis 0.004 close parenthesis open parenthesis 1 minus 0.004 close parenthesis enter, and we get 11.952, which is greater than or equal to 10. So we can proceed on with our hypothesis test. So we can use our calculator to help us out so we're not having to compute the test statistic and the p-value and all of that by hand, which will make this easier. So you can kind of see those computed in the PowerPoints. But anytime we're working with population proportion, we're going to use 1 prop z test for the scope of this course. So any of those tests are when we're performing a hypothesis test. So to get to that, we're going to do stat go over to test, and then look for one prop z-test, which in this case is number 5 on my calculator. So P sub 0 is the population proportion that's in the null hypothesis, so that's going to be 0.004. X is 17, N is 3,000, and we're going to do prop, and it matches up with the alternative, so in this case not equal to P sub 0, and then we'll go down to calculate and press enter. So this is going to be my input. So P naught is 0.004, X is 17, N is 3,000, and then not equal to, so we're good there, and go down to calculate and press enter. So we have several things that come up on our screen. So what are those values that are represented here? So it tells us what we typed in. So it tells us that our alternative has not equal to in there. And then it gives us what we call our test statistic. So Z, if you're reading in the textbook, they use Z sub 0 for their test statistic. And then P, not to be confused with P hat or P naught, or this P, our population proportion. So the P that the calculator outputs is what we call a p-value, which is important. That tells us whether we reject or not reject our claim. And then P hat is our sample proportion, and then N is our sample size here. So this is our alternative hypothesis. This is our test statistic. This is our p-value. This is our sample proportion, our point estimate. We've heard it called before. And then this is our sample size. So what we're really concerned about here are two values. We're concerned about our test statistic and our p-value. So we're going to look at two different approaches here. So let's look at the p-value approach first. It's just a little bit easier here. So p-value approach. So for the p-value approach, what we're going to do is we're going to compare the p-value to alpha. So our p-value is approximately 0.01, oops, too many zeros there, 0.148, and alpha was 0.05. So we compare those. So is the p-value greater than or less than alpha? Well, the p-value is greater than alpha. So when the p-value is greater than alpha, then we do not reject. Right. So the easy way to remember this is when the p-value is low, the null must go. So that's kind of a way to remember that. So we know that we do not reject the null. So that's the p-value approach. So you're just comparing the p-value to alpha. So now for the classical approach. So let's take a step back while I'm writing this. So what exactly is a p-value? Well, that's the probability of obtaining a sample proportion, in this case, or sample mean, depending on what you're working with, as extreme or more extreme than the one that you calculated from the sample. So the one that we calculated from the sample here was this p-hat. So that's what that is referring to. So in the classical approach, what we need to find is what we call the critical values. So we're testing at the alpha equals 0.05. So a couple things we need to look at is our alternative hypothesis was p was not equal to 0.004 and alpha was 0.005. So alpha tells you what's in the critical regions. So this is a two-tailed test. It tells us we have two critical regions. So these are our critical regions. So what I shaded here is our critical regions. So alpha is split between those two regions. So if I do 0.05 and divide it by 2, I have 0.025 in each of the tails. And if I do 1 minus 0.05, I have 0.95 left. So that's in the middle. I need to find the critical value. So this is negative z sub alpha over 2. And this is z sub alpha over 2. Alright? So now I want to find those values. So to find this one, so to find negative z sub alpha, I can use inverse norm. So remember, anytime we're looking for a z-score or data value or a percentile rank, we're going to use inverse norm. So negative z sub alpha over 2, we're going to compute using inverse norm of 0.025, comma 0, comma 1. So anytime we're working with z values, our mean is 0 and standard deviation is 1. So we're going to do second bars 3, 0.025, comma 0, comma 1, and enter, and we get negative 1.96. Well, this is symmetric, so z sub alpha over 2 is just 1.96, right? So now what we want to do is compare that with our test statistic. Well, our test statistic was 1.45. So z is our test statistic, and that was approximately 1.45. So where does that fall? Well, 1.45 falls somewhere here, right? So we can just think about that being on our z distribution. Well, 0 is right in the middle, right? So since our test statistic does not fall in the critical region, that means we do not reject. So we reject when the test statistic falls in the critical region. So we do not reject since our test statistic is not in the critical region. Okay. So now that we've used both methods, let's write out our conclusion in terms of the problem. So since we do not reject, that means that there's insufficient evidence. And to be a little bit quicker, let's type this up. So there is insufficient